Hello everyone, Dr. Zia Tahir here. This video tutorial is solution to problem 1.9 from Mechanical Vibrations by S.S. Rao 5th edition. So this problem is also problem 1.9 in Mechanical Vibration by S.S. Rao in 6th edition. This problem is about finding equivalent spring constant or spring stiffness of system. So the relevant topic for finding equivalent spring stiffness in the book, that is 1.7.4, and that is combinations of springs in parallel. So when springs are connected in parallel, their equivalent spring stiffness is just sum of stiffness of all individual springs. And when the springs are connected in series, equivalent spring stiffness is reciprocal of sum of reciprocal of stiffness of all springs connected. In this problem, so two springs are torsional springs and three springs K1, K2, K3 are translational or linear springs type of problem. So we cannot solve that problem directly using simple series or parallel combinations of spring. And to solve these type of problem, we have to use other methods, and the most suitable method here is using elastic potential energy, because when some rotation is given to the shaft, so due to that rotation, so every spring so that resist, and then with that rotation every spring that has ability to store some potential energy. So elastic potential energy in case of linear or translational spring is half kx squared, and in case of translation rotational springs it is half kt theta square. So k here is spring stiffness and kt is torsional spring stiffness. X is the displacement in translational direction, and theta is rotational displacement. So assumption to solve this problem is we have to assume that theta a small value in radian. So its sine is nearly equal to 0 and its cosine is nearly equal to 1. In this problem, equivalent spring stiff constant or spring stiffness is required in the direction of theta. So that is angle theta, its direction is given. So these two springs straightforward, we can find out their potential energy of each spring. But these two springs, so they are the linear spring, and for linear springs we have to use half kx, and then we need to develop a relationship between x and theta, and we'll use here total elastic potential energy of the whole system is equal to sum of potential energy stored in each individual spring. So total potential energy is equal to potential energy due to spring K1, K2, K3, and then due to rotational spring KT1 and KT2, and then this U of the total is half into K equivalent, and then that theta square will use here, and UK1 is half K1 into x1 squared. I am assuming that uh, like here translational displacement for spring K1 is x1, then half K2 x2 squared, then half K3 x3 squared, and then for both of these springs, because they are on the same shaft, so then their displacement will be for both will be the same, which is theta, and that is going to be half kt1 into theta squared plus half kt2 into theta squared. Now x1, x2 and x3, they are required in terms of theta, and for that we need to develop a relationship that when the shaft is going to rotate with an angle theta, so how much will be displacement in that rod at distance L2 and L1. So I have just drawn only spring K3 here, and then when an angle theta is given to the system, so then there is a rotation, and then translational displacement in spring K3 is x3, and then we need to find that x3 in terms of theta. So when the rod is going to move towards left, so then using basic mathematical expression s is equal to r theta, so then this displacement can be approximated, and that displacement is simply L2 theta. That is simply L2 theta, but this displacement is that is a curved. That is a curved, and then first, basically, we can assume here that x3 is equal to L2 theta. That is a very, very basic assumption. So further, it can be like this curve. It can be converted to a line or linear displacement by further going like that angle is theta. So if that angle is theta, so then x3 here, that will become L2 L2 then theta, and this one will become its cosine component, so cosine theta. And then based on assumption that for a small angle cos theta is equal to theta, sorry I missed that. So for small angle sine theta is nearly equal to theta. So then this cos theta, it can be written like as with the approximation that cos theta is nearly equal to 1. So then x3 here, it will become L2 theta into 1. So that is basically L2 theta. And with a similar sort of assumption, so then x1, that will become L1 into the same angle theta, and for K2 it will be x2, which is equal to L1 into L1 into theta. So x1 is equal to L1 theta and x2 is equal to again L1 theta, because for K1 and K2 the total length is L1 and angle theta that remains same. So then the values of x1, x2 and x3 can be substituted into the original equation. So after substituting value of x1, x2 and x3 square in the equation of potential energy, so it will become half k x theta squared, and then for x1 it is L1 theta 1, for x2 is L1 theta, and for x3 it is L2 theta. So after substituting, it is half k1 L1 squared theta square, half k2 L1 squared theta square, and half k3 L2 theta squared, and then it is half kt1 theta squared plus half k2 theta squared. And now theta squared is a common factor on left hand side. Here all terms have that theta squared. So from right hand side of the equation, half theta square can be taken as common, so that half theta square on both sides is going to cancel. So then equivalent spring stiffness will be k1 L1 squared plus k2 L1 squared plus k3 L2 squared, and then next is kt1 plus kt2. So that is equivalent spring stiffness. So if that equivalent spring stiffness is required in terms of like x, so then probably you have to convert that theta into, you have to write that theta in terms of x. So this is about all about this problem. So thank you very much.